Hi everyone, welcome back to Quantum Mechanics for Everyone video series, and this is the fourth episode of this video series. If you have not watched any of my videos in this video series, I would strongly encourage you to watch all the previous videos, uh, as most of the prerequisite knowledge is there in my previous videos. And if you are very new to this lesson, right, today I think it's my responsibility to quickly go over what we have already discussed. Right, so we use wave mechanics, guys. We already know that to learn quantum mechanics we can take any path. There are just two paths. First one is the wave mechanics, or you can use matrix mechanics, right? So matrix mechanics we put aside for a while, as I personally believe that wave mechanics is more intuitive than matrix mechanics. So we start with wave mechanics. Later on, we can bridge wave mechanics and matrix mechanics, and even matrix mechanics is very powerful. Heisenberg's method, and even Pauli, Heisenberg's, and they contributed to matrix mechanics a lot. But this is actually Schrodinger's main model. This is the Schrodinger's playground, but uh, first of all, I think anyone, a beginner, this is the beginner friendly approach, as I personally feel. So we start with wave mechanics, wave approach. So if you're someone who's going to master quantum mechanics and is still a beginner, you really need to master wave mechanics up to some extent. That's why in my second episode, I derived a very powerful classical equation that will later on turn into quantum uh, quantum models, which is classical wave equation, right? Classical wave equation. This derivation, if you are interested in this, you can watch my second episode of this video series. So I'm going to attach the link in my description. You can go through it and watch this. And classical wave equation looks like this, right? Which is dabba squared y over dabba x squared is equal to dabba squared y over dabba t squared. And here we put v, which represents the velocity of a wave. So this could be any sort of wave, either a progressive wave or a stationary wave, right? And we already know that stationary waves are formed by overlapping or by superposing two waves which are moving in opposite directions, so that this can be any wave. But let me take that if this is a moving wave, yes, this one, so dabba squared y over dabba x squared and dabba squared y over dabba t squared. Now simply this y is a variable, and this is y and this is x, and this equation tells you that y is a variable of x and it depends on displacement, or the x displacement and the time, right? Over time, it's pretty cool, pretty obvious that over time the y displacement changes and depends on the position, the x position, as well as the time, right? And then in my second video, uh, we found out some solutions for this. So now this is in the form of mathematical form, so we can just go ahead and find some solutions. In my second video, I found a proper solution which satisfies this wave equation, right? That solution is fx minus vt. So this f could be any function plus here g x plus vt, right? So even this can be any function of x plus vt. For example, x minus vt is, you can say, a sine x minus vt, sine kx minus vt, or else anything you can choose, ln x minus vt, exponential x minus vt, etc. Anything, right? Anything which satisfies this. can be chosen as a solution. And we don't really want to have both of these terms all the time, guys. Either you can pick one of them. You can just completely get rid of this term, and you can end up with fx minus vt or gx plus vt. Say, alone, any of these solutions still satisfies this one or that one will also a solution for the wave equation, right? Classical wave equation, right? So then, right, let me move on to the most important part of this lesson, guys. We usually recognize this as the forward moving wave. This is the forward moving one, and this is the backward moving wave. But I really want to introduce, and I really want to intuitively show you why we just treat this as a forward moving wave and why we treat this as a backward moving wave. Surprisingly, out of nowhere, we take this as forward moving, we take this as backward moving. Is it so? No, not really. I'm going to show you. This is a backward moving one, but those are not coincidence. I'm going to show you exactly what we are doing with them, right? So now let me consider for a moment. Imagine you have got a, yeah, this is the y displacement and this is x, and there is a wave, and I don't know what exactly the function is. This could be any function, guys, but for simplicity, let me take it as a function like this. It is, let me take right, the function here x minus vt, and here it is, let me take a k times, k is a number, I don't know, k times x minus vt would look like this, right? And now here, let me take the displacement at this point. This is my x naught, and this is somewhere here we can find, sorry, this is x1, here somewhere here we can find x2, and somewhere here we can find x naught. Right, now imagine if the wave profile propagates, or if the wave profile moves in this direction, forward direction, guys, right? So this is where you can find the wave profile, the same wave profile, right? After a while, after a moment, you can find the wave profile somewhere here. So with time, we already know that this time is always increasing, guys. Imagine if this is the let me take it as amplitude or a or something like that. If the displacement obtained by the wave at this point is a, right, this particle when the wave propagates is a, right, I can just say that, so this is not, this is y, and this y can be replaced by this a now is equal to this is k. K is a constant, guys. For simplicity, I took it as a constant. You can choose any function you want, but I think this is just a pulse, not a wave, for simplicity. And for clarity, I took it as like simply a pulse like this. And here now x minus vt, and imagine now previously the time is t1, and imagine time increases, oh, right? So time increases. So then imagine at the second moment when the wave moves to this point, right? Imagine if it is a forward moving wave, right? Or else we don't really know whether it is forward moving, right? But when the, right, here it was x1, right? When the wave propagates, the time increases, we already know that. So now the new time would probably be t2, it's higher than t1. But if you really want to end up with the same a, right, so x1, now here there's a subtraction part, guys, x2 has to increase, or simply the x value should be higher than previous x1, then only we can end up with the same a, because now this is vt2 is higher than vt1, right? So that if you want to have the same a at this point, definitely, right, so x2 should, or x2 has to also increase, right? So therefore this is definitely a forward moving wave. So then we can conclude that this model represents a forward moving wave. Cool. Right. So then I know you are smart enough to figure out that this is a backward moving wave. You can try it as homework. I'm not going to do it here. I think you can use the same technique, same method. So you'll be able to end up with, you will be able to finally conclude that this is a backward moving wave. Right? Okay. And then I think we're done with that. Let me go ahead. Now, any solution we can pick, any solution, but let me choose a very simplified general classical solution like this, guys. So most of the time uh, we prefer sine, cos and exponential functions over other functions for some reason, guys. Even in wave mechanics, when we dive deeper into waves, when we learn more about waves, guys, we try to stay away from, we try to avoid other functions, but we simply prefer these exponential functions and sine cos functions more than other functions, right? The reason is, now let me take few functions like this, guys. So first of all, sine x minus vt, or cos, I can write if you want cos x plus vt2, and sine x minus vt and cos x plus vt, guys, these, they have a value everywhere, in the sense no matter what this part is, plus or minus, right? So those are continuous, you can find values, right, unless they're in zero. So whatever the value is, no matter what, you can always find an outcome, a value. But imagine if you replace them with some functions like ln, right? ln x minus vt, or tan x plus vt, or something like that, right? Still they satisfy the wave equation. Still there are solutions for this classical wave equation. But the problem is, ln, as soon as it becomes negative, you will be in a deep trouble, because negative values for this function cannot so they cannot they don't exist. Therefore you can't really find what the solutions are, right? So they don't actually, there are some limitations locally, global in the sense of, if you generally consider, yes, some values exist, but locally sometimes this will lead to some confusions. We have to avoid these confusions as much as we can. Even tan is fine, but you already know that when tan goes to 90, right, the solution goes to infinity, which again bothers us a lot, because we can't really find what sort of outcome that is. So though they have solutions, though they are also uh, fine, they are also providing some solutions to us, we keep them aside, because we have some fundamental solutions like this, and even exponentials like this, right? And even we can choose e to the power ik, something like that, I x over x minus vt, and even this is a very fundamental equation that most of the time we use in quantum mechanics. And these are well behaved, right? So the integrity is much higher, guys. So that's why we choose these sort of functions over other functions specifically. And then something I really want to emphasize is, if you have ever noticed this one, in quantum mechanics, guys, exponentials are everywhere. Not just exponential, some uh, imaginary exponentials like this. So why do we prefer these exponentials? Why do they show up everywhere in quantum mechanics? And also I really want to derive this one, because we don't really like it like this. Now imagine y xt, right? Imagine you have a function like this, sine x minus vt plus cos x plus vt, right? So now you already know that v is equal to, we have already derived that v is equal to omega over k. And imagine now, instead of just writing it this like this, if I just modify this equation a bit with the k, sine k, and even still this satisfies, because even if you put this constant k in front of this number, this is still a function which behaves like this, f, then here sine k x minus vt plus here cos k x minus vt, right? So we can write the wave solution like this. We can deliberately write it like sine k here x minus vt. Now v can be written as omega over k times t plus cos k x minus omega over k times t. So now we can put this k into the bracket. So we'll end up getting sine kx minus omega t plus cos kx minus omega t, right? So this is a very useful solution and a profound solution that you can use to describe any classical wave. And also with the help of Euler's formula, guys, we can even use exponentials to write same sort of solutions. So with I, if I write an exponential solution like this, kx minus omega t, you can still write this like sine kx, because Euler's formula, if you don't know what the Euler's form is, guys, so that is e to the power I theta. If you ever come across these imaginary numbers, if you are not familiar with imaginary numbers, don't worry. So I is equal to minus 1 square root. Actually, you can't just define it with other numbers than imaginary I. So that's the only number that you can use to define this square root minus 1. So in the Euler's form, guys, you can write it like sine theta here, sorry, my bad, cos theta plus I sine theta. So I'm going to do the same now. You can even write this solution, right? So even if you ever come across something like this, e to the power I kx minus omega t, you can just go ahead and write it like this, cos kx minus omega t plus here I sine kx minus omega t. And even this is a perfect solution. I mean, this one, as in this is a very good solution, and we frequently and we more often come across this one everywhere in quantum mechanics. But why quantum mechanics prefers this exponential solution? There's a deep reason for that, guys. So let me rest the other side. I want to get ready. I want to make this side ready to our next ultimate task, which is this one. And operator mechanics, I just want you to introduce quantum mechanics operators, right? So what you need to understand is the quantum mechanics is not like classical mechanics, guys. In classical mechanics, we have direct values. Momentum has a value, P equals mv, kgm is minus 1. You can just write what the value is. Kinetic energy has a value, total energy has a value. Those are value based numbers. But quantum mechanics, guys, mostly relying on operators. We don't straight away throw values like this in quantum mechanics. So we can't do that, right? And you will properly understand this later on when I dive deeper into Schrödinger equations. I'm going to derive Schrödinger's equation in my 5th episode. So then you will understand why we basically use these things. But just for sake of understanding, I'm going to use, just for sake of um, yeah, understanding these wave mechanics properly, I'm going to show you why we mostly prefer these exponential terms, x minus omega t, even you can write it as plus sometimes, depending on the context, right? So because in quantum mechanics, every particle every particle uh, can be treated as a wave at a certain instant. So unless we measure, unless we detect it, right? This is not the deeper meaning of this one. Just for sake of this clarification, I use this, right? You can just treat it as a wave, guys. So you will understand later on, because in my next video, in my second chapter, sorry, in my fifth episode, I'm going to show you some bizarre observations that you can't ever explain using classical mechanics. So then here we use some sort of wave functions to explain the nature of those quantum particles, right? So then you can use phi x. Actually, it depends on time too. Now this is very similar to that yxt, if you remember. So this is a function which depends on time and the position, right? So, and the next important thing is, in quantum mechanics, when it comes to some particular operators, for example, momentum or uh, the Hamiltonian or any sort of operator, we have plenty of operators, right? So there are some eigenfunctions. So eigenfunctions have a good correlation with these operators. Why? Because if you put an eigenfunction in front of, so in eigenfunctions, so and keep that in mind, not all the functions are eigenfunctions. It is okay not to be an eigenfunction too, right? Imagine if you choose a function that is not an eigenfunction of an operator, of a given operator. It doesn't matter. Not every function is an eigenfunction in quantum mechanics. But there are some selected functions, they are simply eigenfunction of given operator. For example, so this is what they look like. If you put an operator in front of this phi xt now, phi xt, you will still end up with the value lambda and here function itself again, right? So this is very important, as right, as now this is the operator. Let me introduce what these terms are. So this one represents the operator, or actually momentum, or a. So a, actually here I chose the momentum previously, but you can choose, this is any operator. A could be any operator, and this is the whatever the function is. Now if you can write it like this is simply an eigenfunction. But if you can't write it like this, not every function satisfies uh, this format. So some functions can't ever be written like this. So those are not eigenfunctions. But if you find out an eigenfunction, you can just write it like this. So this is an eigenfunction. So lambda is called the eigenvalue. It's a value, actually. It's a scalar value, just the magnitude of this whatever the operator is, right? So this is the eigenvalue, right? And this is again the function itself, and this is the eigenfunction. Now you can clearly see that if you put the operator in front of the function, if it is an eigenfunction, you will straight away get a value. For example, if this is momentum, this lambda is the momentum operator. The lambda represents the momentum of this particle, right? If this is the Hamiltonian, this one represents the energy. It's like that, right? So it follows the relevant operator, right? So now imagine now I chose the, right, I'm going to show you one example. So I'm going to choose the momentum operator. if you have never seen the momentum operator before, I'm going to introduce what momentum operation is. That is minus I h bar here, dabba over dabba x. You already know that what the dabba terms represents here. So, and now, right now, let me take my function as this one. Now imagine there's a particle. You don't know what the particle is. I don't really want to define what the particle is, but there's a specific particle, phi, right? It obeys this wave function, phi xt is equal to exponential I x minus omega t. Oh, my bad. Here k, I should put kx minus omega t. Kx minus omega t is the function of this one, right? Right. Now, what if I put this operator in front of this? Let me take a moment and give it a try, right? So now minus I h bar dabba over dabba x, exponential here I kx minus omega t. Let's check it out. Now, when you simplify this one, you will definitely end up with something like this. Minus I, you can keep it as it is, right? And h bar, you can keep it as it is. And now the dabba forces you to take x as a variable and t as a constant. Though t changes over time, with time, here we assume or we treat it as a constant. So what we end up here is now times here I times k, and again when you get the first derivative of this function, again exponential I kx minus omega t, right? This is something very important. Let me move on to the other side. Now if I just recall what we have got here, right? So now we have a term like this, minus I and h bar times again I, and here k, and here e, here I, here kx minus omega t. Can you see, guys, that this is the function itself? This is phi xt, and here we have minus, sorry, I to I squared. We already know that minus I is equal to minus 1 square root, so I squared is again minus 1, so that this will lead to minus 1 times minus 1 is equal to plus 1, so we will end up with h bar k exponential I kx minus omega t. Something very, very fascinating has just been derived. Why is it so important, guys? If you carefully look at this, guys, this hk represents the momentum itself. If you're someone who has just completed your high school, I think I should help you a bit with you. Now h bar is equal to 2 pi over k, guys. Sorry, h over 2 pi. And here k is equal to, you already know the wave number, which is 2 pi over lambda, right? So now h bar k is equal to h over 2 pi times here 2 pi over k. So you will end up with h over k. What is, sorry, my bad, here lambda, sorry, h over lambda. So then this is h over lambda, right? So if you remember the Planck's relationship, guys, that you have in high school, right? So Planck says that momentum of a particle, a tiny particle, is equal to h over lambda, right? So this is the momentum itself. So now what we got is, when you put the operator p for in front of this one, we ended up with the momentum itself p because this one is the momentum. H bar k is the momentum itself times, again, 5, this our function. This is a perfect eigen function. In a matrix mechanics, guys, we call them as eigenvectors, but here eigenfunctions, right? So that's why this is most of the time this e to the power ikx minus omega t is an eigenfunction of momentum operator. So we mostly prefer these sort of exponentials just because of that reason. Just keep that in your mind. This is very, very important, guys. Right. So now we are familiar with most of the uh, functions, and quantum mechanics completely rely on these sort of functions. You should really master these stuff, and later on I'm going to solve some really important questions with you too in this series. Hang on, guys, and I would yeah, I really want your cooperation and your support to continue this lesson, this series. So keep in touch. See you with next video. Thank you very much for watching. Bye bye.